Okay, and the masked professor is on once more. This is the April 30th edition of Introduction to Engineering. I am, of course, your genial host, Harry Whiting. All right, so today we're going to talk about civil engineering. They give us three different parts of the slideshow for civil engineering, but I'm only going to show you two. The first part is about structural engineering. Okay, so we are going to talk about a little bit at least. Part 1, structural engineering. Part 2, geotechnical engineering. And part 3, water resources engineering. All right, so the first part of Part 1, structural engineering, is about truss structures and the method of joints. So we're going to talk about structural elements, free body diagrams, and the method of joints. And how we solve large problems. Structural elements, when we're talking about bridges, they are a bunch of structural elements put together. The elements are characterized by their geometry and the forces acting upon them. There are different types of elements ranging from plates and shells to springs. But we're only going to talk about three kinds of elements: beams, compression members, and tension members. All right, so this is a bridge over a chasm in Northern Ireland, and only has tension elements, right? So you can see here, obviously this is just a walking bridge. This is much fancier than a Boy Scout rope bridge, but you can see everything there is in tension. So when we say everything is in tension, there's some distance in between these two points. We have a load on the bridge itself. There is some amount of deflection from that load, and we have a free body diagram where we show our load and the tension on both sides of the bridge. Okay, so when we solve these kinds of problems, we have to remember that the amount of force going this way in the negative x direction, the amount of force going in the positive x direction have to be equal and sum up to 0. Similarly, the forces in the y direction, so the force of this coming down and the amount of force in the y direction going up here and the amount of force going in the y direction up here all have to match. Or they have to add up to 0, I should say. All right, so in general, we say that a beam deflects under load. We often draw it in a very exaggerated fashion, like this dotted line here, when in fact a lot of times we can't see with the naked eye how much deflection is happening. So here is a free body diagram of the situation illustrated up here at the top. Right, so you have car 1, car 2, car 3, car 4. The total amount of load from these 4 cars has to be exactly equal to the reaction load at A plus the reaction load at B. Now, they use this pier as an example of a compression member. In this case, you have a reaction here and here, but you also have a reaction here from the load represented by these 4 cars. This dotted line shows in exaggerated form the deflection and reaction loads and what effect they are having on our bridge. Now, we can continue that and say sometimes we have a beam where we have tension members like a suspension bridge. So we add these 2 tension members, and you'll notice that once again our dotted line showing which directions the force are going in has changed again because of the tension members. All right, so we say what kind of structural elements are shown here? Here we have a gusset plate. You'll notice this is riveted together. A lot of times large structures like this are, sometimes they're bolted instead of riveted, but very often they're welded. Rivets have an advantage though in this kind of structural design because they fail very slowly compared to welded elements. All right, so our trusses may have many connected members. It's going to be composed entirely of tension and compression members. They want it to be triangulated for the live load and the dead load. The live load is traffic or pedestrians. The dead load is the weight of the members themselves. And we solve that, what the tension and compression members will be carrying, by using the method of joints. which we're going to get to in a minute. All right, so we see a couple of examples of truss bridges here. Here you have a truss bridge. Notice everything is broken into triangles, right? A triangle is the strongest shape we know for a situation of this type. Here we see the same thing. Now, if they had chosen to make X's in each of these places, the equations for the bridge would be much harder to solve. All right, so the method of joints is what we use to find the unknown forces in a truss structure. The principle behind this method is that all forces acting on a joint must add to zero if the joint is to remain stationary. So the forces don't add to zero, it moves. It adds to zero, stays there, everything's okay. We do assume that all the members are joined by frictionless pins. In other words, each beam or piece of the truss is expected to just have pure forces going through it. Equations of static equilibrium can be written for each joint, and the set of equations can be solved simultaneously to find the forces acting in the members. All right, so in this case, we have two members. We have a force right here of 10,000 pounds force. And we want to find out what are the forces in the members. All right, well, first of all, our pin B has 10,000 pounds force pushing down on it, the load. It has a force in the direction of AB and a force in the direction of BC. Okay, so AB, BC. We see then we have our AB here as a separate illustration, our BC here as a separate illustration, right? And you'll notice that we are obeying Newton's law that for every force there is an equal and opposite force. Okay, so fantastic. So let's go to our next. Now, what do we do? Well, in this case, there are only two unknown forces. The force in AB and the force in BC. We can write two separate equations where the summation of the forces in the x direction equals 0, which they've done here, and the sum of the forces in the y direction equals 0, which they have done right here. All right. Now, because we have two unknowns, that those are the force in AB and the force in BC, and two equations, algebraically, we can solve that equation. All right, and when we do, we see what our force AB is and what our force BC is. We do have a problem though. If we want to solve for a whole bridge, we have to go through and do those same calculations for every joint in the entire bridge. These guys suggest using a matrix solution. Now, you can find on the internet you can find programs that will solve bridge trusses. All right, so we we break down the structure into its compression and tension elements. We draw a free body diagram. For truss structures, we use the method of joints, although we could have also used the method of sections, but they thought that was too difficult to take on in this. We solve for the unknown forces in the structure. And again, for large structures, we are going to generalize our solution and make a matrix and solve the matrix for our structural forces. Okay, well, wasn't that exciting? So, part 3 of chapter 8 about civil engineering is about water resources engineering. We have a whole bunch of water resources distributed around the world. And you'll notice they're saying the northern hemisphere is just pretty well supplied with water. And gosh darn it, we're happy about it. The problem is, if you notice here, the tiny New Mexico is saying we've got little or no water scarcity. Ha! Oh, I mean, that's not true in this case. Okay, so because this is such a small scale map, it's probably got some problems with representation of particular spots. All right, so when we talk about water reservoirs, we worry about the geometry of those and the capacity. our water capacity is in units of volume, right? So sometimes you'll hear you'll hear the bigwigs talking about acre feet or cubic feet of water or cubic meters. All right, so we see the reservoir from the top. There's a stream that feeds it, and it's essentially a triangular situation. We look at the side view, we still have a bit of a triangular situation. And here's the stream feeding it, of course. And then when we look at the front view, we see that we are seeing the dam still in a triangular situation here. Okay, so triangles rule the day, apparently. So for this particular reservoir, the volume, V, equals 1/6 length times width times height. And it's 1/6 because of using all these triangles. Generally, they're going to say that the volume equals C1 times C2 times H raised to the third. C1 and C2 are going to be constants peculiar to each dam that regulate so that we only have to have one measurement of height to explain the volume or capacity. All right, so they want us to develop, in this example, develop an expression that relates the instantaneous height of the water level at the reservoir to the volume of stored water. Assume reservoir dimensions of H equals 100 feet, W equals 300 feet, and L equals 3,000 feet. And then 15. All right, so we need an expression for the stored volume, VS, volume stored, in terms of instantaneous depth, H. The proportions of the reservoir, H equals 100, W equals 300 feet, L equals 3,000 feet, and V equals 1/6 LWH. Which, of course, works out, well, maybe I shouldn't tell you. I'll just tell you the first two numbers are 15. All right, so how do we derive that equation for the volume of water in a partially filled reservoir, recognizing that the dimensions of this smaller volume have the same relative proportions as the completely filled reservoir? First, let the dimensions L, W, and H of the partially filled volume correspond to L, capital W, and capital H of the filled reservoir, respectively. Since both volumes have the same relative dimensions, we know that L divided by H equals L divided by H equals 3,000 divided by 100 equals 30. Then we say that W divided by H equals capital W divided by capital H equals 300 divided by 100 equals 3. Therefore, our volume of stored is 1/6 LWH equals 1/6 30H times 3H times H, or 15 H cubed. Now, in my head, I went ahead and worked out the whole thing, and it works out to be 15 million cubic feet. All right, conservation of mass. We talked about conservation of energy earlier in this course, and we've talked about conservation of mass. Terms for water flow can be added, removed, and or stored in the reservoir. So the change in the mass stored equals the change in mass in minus the change in mass out. Right? Things that can come into the reservoir might be rivers, rain, snow melt. Things that go out might be agricultural use. We're using it to power energy, things like that. Here, they're planning on plotting expected water storage over the time span of the historic record. And it allows for negative storage. So, this model assumes that our input source, a certain amount of that is allowed to pass through. Well, I would say that, but let's just go with it's an absolute number. So the inflow is 2.36 times 10 to the 9th cubic feet. Demand is 3.11 times 10 to the 9th cubic feet. That means we end up with a negative 0.75 on our net inflow times 10 to the 9th cubic feet, or billion feet cubed. All right, so our cumulative storage in this case is a negative 0.75. In the second month, we get an inflow of 2.49, a demand of 2.85, so our net inflow is negative 0.36, and our cumulative storage is negative 1.111. Excuse me, negative 1.11. I put one too many ones. Now, the reason that I say there must be some volume in the reservoir already before we even consider month one is, how can you have negative cumulative storages, right? If there was no water in before our inflow and our, how could we meet our demand, which is bigger than our inflow? All right, you can see that in the third month, inflow is 1.66. Demand is 3.37. Oh, bloody hell, that's twice as much. So our net inflow is negative 1.71, and our cumulative storage is negative 2.82. All right, let me skip to month 5, which would be May if this follows the January to December paradigm. In month 5, we have an inflow of 13.58 trillion cubic feet. Our demand is 3.89 trillion cubic feet. Therefore, our net inflow is 9.69, which means our cumulative storage goes up to 5.86. So we did well in that month, and you'll notice that for the rest of the month, we get low, but we never go into negative territory again on our cumulative storage. All right, well, bloody hell, I'm not just going to read this table to you. That's boring for you and for me. Instead, I'm going to go to the next slide. All right, so our need is to have the water storage plotted as a function of time. We know the monthly values of inflow and consumer demand for a 12-month period. How do we know this? We calculate how do we do this? We calculate the net inflow for each month, then for each month add storage increments up to and including that month's contribution to define cumulative storage values as per m raised to the n stored, which is equal to the summation of m raised to the I stored. All right, so our results, which were shown in the table, can be shown in Excel without use of special functions. All right, so here they're showing us our cumulative storage. Month 1, we're a little negative. 2, we're more negative. 3, we're even more negative. 4, we're really getting negative. Then month 5 makes us well again and continues on out through month 12. Our estimation of required capacity and yield. Yield is calculated as the average inflow over a span of time, which is often taken to be the period of lowest inflow from the stream on record. So our Y equals 1 divided by m, with m being the number of time intervals. We do a summation from I equals 1 to m of the change of mass in month I inflow, and we divide that whole expression by the change in time. See, easy peasy, lemon squeezy. Our yield basics are cumulative storage versus the time plotted over a period of, say, 4 years as per next figure. Oh, okay, that's helpful. So our subsequent peaks, P1, P2, P3, and their corresponding minima, M1, M2, M3, have been indicated. the sequent peaks are defined such that P1 is less than P2 less than P3. All right, so here they show us the figure where we have P1 hits a maxima, P2 hits a maxima, P3 hits a maxima, and these low points at M1, a minima at M1, a minima at M2, and a minima at M3. All right, so we are showing our cumulative storage, in other words, the inflow minus demand summed over time. So from that we can estimate our required reservoir capacity. All right, so we have we need the reservoir capacity based on the figure. We know that we have 4 years worth of historic data for cumulative storage. First, we identify the sequent peaks in orderly progression and associated minima by reference to the figure. Then we compute the difference between each subsequent peak and its minima. The largest difference is the required capacity. All right, so where is the largest difference? Looks like it's between M1 and P2. Well, possibly P3 and M3. But since there's a dip and then another peak there, I'm not sure how to take that. Okay, so they're calculating it as the peak 1 versus minima 1, right? That turns out to be 6.46 trillion cubic feet. Between peak 2 and minima 2, that's 611 trillion cubic feet. And peak 3 and minima 3 at 9.44 minus 2.27, giving us a difference of 11.7. Therefore, the capacity we want is 11.7 trillion cubic feet. Takes a while to empty that bathtub. All right, so you've seen what we've done here, where we did a simplified estimation of the size of a reservoir, conservation of mass, capacity and yield of a reservoir, and the sequent peaks analysis. How sequential of them? Are there any questions? Okay, I have put these, the PDFs of these in the Moodle, where you can access them. You will have a link to this video and the other videos in Moodle, and the assigned homework is in there too. Okay, so I want to say one thing about civil engineering that isn't really in our book or the slideshow presentation. when I was at Ohio University, I worked for the Ohio University Traffic Engineering Group. I was their human factors guy. And so what we did there was kind of traffic engineering things. So I was the human factors guy. I studied why people act like they do in cars. We had other people that were measuring other aspects of human driving, right? I guess that falls under structural engineering because roads are built in accordance with what the traffic engineering guys decide on. Okay, well, stay healthy, stay safe, and when the fields are white with daisies, we'll meet again. Bloody hell. There you go.